Hello, welcome to another module in this massive open online course. So, we are looking at example problems in Fourier analysis. Let us continue this discussion. All right. So, we are looking at example problems in Fourier analysis. And what we have seen previously, I mean we are currently looking at the Fourier series expansion of this periodic triangular wave, and we have seen this triangular wave. If you look at the derivative, that is x prime t, and consider x tilde t which is half plus x prime t, or I am sorry, x prime t is we have x prime t, okay, x prime t, and if we consider x tilde t which is half plus, I am sorry, I need to x tilde t which is half plus x prime t, that is given by this periodic square wave that we have seen earlier. Okay. So, we have x tilde t is x prime t plus half, and therefore, x prime t, that is the derivative of x t, is x tilde t minus half. Now, we know the CFS of x tilde t, we have already defined or we have already derived the complex exponential Fourier series of x tilde t and the complex exponential Fourier series of x tilde t. This is given as half plus 1 over j pi summation m equals minus infinity to infinity 1 over twice m plus 1 in fact times e raised to j 2m plus 1 omega naught t. This is the complex exponential Fourier series of x tilde t. Therefore, this implies the CFS, the complex exponential Fourier series of x prime t, which is equal to x tilde t minus half, that is equal to, now subtracting half, you can readily see that that is 1 over j pi, simply m equals minus infinity, m equals minus infinity to infinity e raised to j 2m plus 1 omega naught t by 2m plus 1. Okay. And now what we have is now, so we have derived the C, so we have been able to derive the CFS, the complex exponential Fourier series of x prime t. Now also realize that x prime t is nothing but the derivative of x t, okay, and we have already seen this, that is if we have the complex exponential Fourier series of x t, or let us look at this, let us say the complex exponential Fourier series of x t, which is the triangular wave, let the CFS of x t, which is the original triangular wave, x t equal to, let us denote this by summation k equals minus infinity C k e raised to j k omega naught t. Now, this implies the complex exponential Fourier series of x prime t, which is equal to d, that is the derivative of x t, that will be given as, now if you differentiate this, you have summation k equals minus infinity to infinity. If you differentiate this, you have j k omega naught, correct, you have j k omega naught c k e raised to j k omega naught t, and this is basically your c tilde k. You can call this coefficients of the complex Fourier series of c tilde k. Now, let us call this as expression number 2, and we already have an expression for this complex exponential Fourier series of x prime t from above. Let us call this as expression 1. Now, from expression 2 and expression 1, comparing the coefficients, now because both of them are the complex exponential Fourier series of x prime t or the derivative of x t, from 1 and 2 what we can do is we can compare the coefficients. Because both are the complex, correct, what we are doing is we are comparing the Fourier coefficients of the complex Fourier exponential Fourier series, because the CEFS, because the complex Fourier exponential Fourier series represent, because both give us the CEFS of x prime t. So, what we can conclude is that the coefficients must be equal, in particular the coefficients of the terms e raised to j k omega naught t. So, what we have is, comparing the coefficients, we have that this coefficient c tilde k must be equal to this coefficient of e raised to j 2 m plus 1 omega naught t, or in other words we must have c tilde k equals coefficient of e raised to j k omega naught t, which is basically, if you look at that coefficient, that is nothing but 1 over j pi times 1 over 2 m plus 1. But remember, as you can see from above, c tilde, recall c tilde is nothing but j omega naught k c tilde. Okay. Now, therefore, now of course, this, remember this is c tilde, okay, this is c tilde k, this is only for k is even or k equal to 2 m plus 1, this is only for k equals odd, sorry, this is only for k equal to odd, that is 2 m plus 1. If k is even, you can see c tilde k, because this exists is only defined, that is a CFS, you can see of x prime t contains only the coefficients corresponding to odd k, that is k of the form 2 m plus 1. So, we will have c tilde k equals, if k is even, we have c tilde k equals 0 implies j omega naught k c k equals 0 implies c k equals 0 if k not equal to 0. Okay, this is the story for k not equal to, if k is not equal to 0, then this implies that it has to be the case that c k equals 0. On the other hand, for c tilde, for k is even, we have c tilde of 2 m plus 1 equals 1 over j pi 1 over 2 m plus 1, which implies that you have j omega naught k, which is 2 m plus 1 c tilde or c of 2 m plus 1 equals 1 over j pi of 2 m plus 1, which implies c of 2 m plus 1, where k is odd, k is 2 m plus 1 is 1 over, this is 1 over minus pi into 2 m plus 1 square, 2 m plus 1 square into omega naught, and this can further be simplified as 1 over minus pi 2m plus 1 square omega naught, remember, is 2 pi by T naught, which implies that C of 2m plus 1 equals minus T naught over twice pi square 2m plus 1 square. So, this is the result that we have relating to regarding the coefficient C 2m plus 1, and Ck is 0, by the way, if k is odd. Okay. So, we have the coefficient C, we have derived the expression for the coefficient Ck. So, the coefficient Ck in the complex exponential Fourier series of the original periodic triangular wave, and Ck is 0 if k is odd, and if k is even, that is k is of the form 2m plus 1, then we have derived this expression for C of 2m plus 1. And the only coefficient that is remaining now is C naught, because remember we cannot derive C naught using this technique, because C naught, when you differentiate x t, remember the DC component C naught, which is a constant, that vanishes. So, that you cannot derive that using the from the derivative, that is x prime t. So, what we do for that is we simply evaluate the DC coefficient. Remember, the DC coefficient C naught equals 1 over T naught integral 0 to T naught x t dt, which is 1 over T naught the area under x t, which if you can see, this is a triangular wave in an interval of duration T naught. In a triangular wave, the area is half base into height, that is half into T naught into T by 4. So, this is simply going to be 1 over T naught into the area, half into T naught into T naught by 4, which you can basically see is T naught over 8. Okay. So, the C naught equals T naught over 8, and therefore, the CEFS of x t the CEFS of the original triangular wave, that is x t, is T naught by 8 minus T naught by 2 pi whole square summation m equals minus infinity to infinity e raised to j 2m plus 1 omega naught t by two m plus 1 square. So, this is the CFS of the original triangular wave, periodic triangular wave. This is a complex exponential Fourier series of the periodic triangular wave. Alright. And now again similarly one can readily evaluate the TFS, that is a trigonometric Fourier series, and the TFS is given as, now coming to the TFS, remember we have A naught by 2 equals C naught equals T naught by 8, which implies A naught equals T naught by 4. Now, A k for k not equal to 0 equals C k plus C of minus k. Now, of course, if k is odd, C k C minus k equals 0, this implies A k equals 0. Now, if k is even, what will happen is we have A k equals, well, we have a k equals, or I am sorry, if k is even, okay, if k is even, c k c minus k are 0. If k is odd, we have a k equals, that is k equal to is of the form 2m plus 1, then a k or a of 2m plus 1 equals, well, this is minus T naught by 2 pi square into 2m plus 1 whole square plus c of minus k, which is minus T naught over 2 pi square minus 2m minus 1 whole square, which you can see is basically minus twice T naught by 2 pi square into Tm plus 1 whole square, which is equal to minus T naught by 2 pi square, I am sorry, minus T naught by simply pi square by 2m plus 1 whole square. This is your a 2m plus 1, okay. So, this is your a 2m plus 1, and similarly now coming to bk, bk equals j ck minus c minus k equals 0 if k equals even, because if k is even, then ck and c minus k are both 0. So, bk is 0. If k is odd, then bk is bk is basically j times well, minus T naught by 2 pi square 2m plus 1 whole square minus T naught or minus c minus k minus minus T naught by 2 pi square minus 2m minus 1 whole square, which you can clearly see is 0. So, b of 2m plus 1 0, which implies bk is 0 for k even or odd, which means bk is 0 for or k. Therefore, the TFS of the periodic triangular wave xt T naught by 8 minus summation m equal to 1 to infinity T naught square by pi square into 2m plus 1 square into cosine 2m plus 1 omega naught t. That is your TFS. This is the TFS of the periodic triangular wave. This is your TFS of the periodic triangular. Okay, so that basically completes. It's slightly elaborate, the procedure to derive it is slightly elaborate. It's more simplistic and more intuitive than trying to rather the direct approach of deriving the CEFS and TFS, that is trying to employ the triangular wave and trying to integrate the triangular wave by multiplying by the various complex exponentials or the various harmonics and integrating to derive the various coefficients of the CEFS. Okay. So, slightly is an interesting and a very intuitive approach, that is to consider the derivative of the triangular wave, which is a square wave, and then approach the CEFS from that angle. Okay. All right. Let us proceed to the next problem. The next problem is fairly simple, but yet again another intuitive problem, that is problem number 5, and this problem is regarding periodic convolution. Now consider, so periodic convolution, now consider two signals x1t and x2t which are periodic. With common period T naught. With a common period T naught. Now periodic convolution is defined as the periodic convolution of these two signals with a common period T naught is x tilde t equals x1 t convolved with x2 t, and this is the symbol for this periodic convolution. Okay, so this is your periodic convolution, and this is done over this convolution basically over a period, over any period, that is x1 tau x2 t minus tau. So while in the conventional convolution we are integrating from tau from minus infinity to infinity, remember this is for two periodic signals with a common period T naught, and the integration is over only one period. Okay, the integration is over only one period. Okay, and now let us derive a property of this periodic convolution. Now what we want to do is derive the CEFS. Derive CEFS of x tilde t given the CEFS of x1 t and x2 t, that is, let us say x1 t equals summation k equals minus infinity to infinity dk e raised to j k omega naught t, x2 t equals summation k equals minus infinity to infinity e k e raised to j k omega naught t. Then now remember x tilde t is simply the periodic convolution, which is integrals over one period 0 to t naught x1 t or x1 tau x2 t minus tau d tau, which is integration over one period x1 tau. Now instead of x2 tau you substitute the CEFS, so that gives us summation k equals minus infinity to infinity e k e raised to j k omega naught t minus tau d tau, and now you interchange the summation and integration. And that gives us, and if you interchange that, that is if you interchange the sum and integral, that gives us summation k equals minus infinity to infinity e k integral 0 to t naught. Well, let us write it this way, we can split the e raised to j k omega naught t. So, e raised to j k omega naught t that does not depend on tau comes out of the integral. What is remaining is 0 to t naught x 1 tau integral x 1 tau e raised to minus j omega naught tau d tau, and you can now see this quantity which is nothing but integral x 1 tau multiplied by e raised to minus j k omega naught tau d tau over 1 period tau naught is nothing but the complex exponential Fourier series of the complex exponential, that is the CEFS coefficient of x 1 tau, that is the kth coefficient of the complex exponential Fourier series of x 1 tau, which is nothing but your dk. So, and this is in fact not dk, but this is in fact t naught times dk, because you can see dk equals 1 over t naught tau naught t naught integral 0 to t naught x 1 tau e raised to minus j k omega naught tau d tau. So, this is in fact your, so this is in fact t naught dk. So, finally you get this is summation k equals minus infinity to infinity t naught dk e k e raised to j k omega naught t. This is the complex exponential Fourier series, which implies that if you have the complex exponential Fourier series coefficients, if you have the complex exponential Fourier series of this as k equals minus infinity to infinity c tilde k e raised to j k omega naught t, we would have t naught dk e k equal to c tilde k, which implies c tilde k, the complex exponential Fourier series coefficient of x tilde k, which is the periodic convolution of x 1 t and x 2 t, is t naught e k dk. This is the CEFS coefficient, kth CEFS coefficient . Of periodic okay, this is the kth CEFS coefficient of the periodic convolution of x 1 t and x 2 t. Alright, so that completes, basically that completes our discussion of examples for the discrete Fourier series, that is the complex exponential Fourier series and the trigonometric Fourier series of continuous time periodic signals. In the subsequent module, that is starting with the next module, we will look at examples for the Fourier transform, that is the Fourier expansion for, or the Fourier analysis for continuous time aperiodic signal. Alright, so we will stop here and continue in the later modules. Thank you very much.